Yes, hello. Is this audible?
Yes, ma'am.
All right. So only you are here. What about the other students? Did you people receive the meeting ID today?
Yes, ma'am, we did.
You have received it. Fine, then let's start because if others have to join, they'll join. So in the last class, yesterday we had stopped till here. The resistance, how to calculate resistance, and we had seen two terms, resistance and resistivity. Now see, in today's class, we'll see more new terms. Some more terms are left, which come in your exam, but they have a very short marks. They have the weightage is very short. So first term is conductance, second term is conductivity, and we'll see two more terms. Two more terms are there. Now, what is meant by conductance? So conductance is basically whatever you studied no for resistance. It's the inverse of it. So conductance is the inverse of resistance. Whatever you studied for resistance. This is denoted through the symbol G. Capital G is denoted for the symbol conductance. And inverse of resistance means 1 by R. So, can you tell me what should be the SI unit of this conductance?
1 by ohm.
1 by, exactly. That becomes ohm inverse. So, these kinds of questions, these are very short questions. They are usually rarely asked, or if they are asked for 1 score or 2 marks question. So just keep in mind 4 terms we use. So first one is conductance, second term is conductivity. Now conductivity is the inverse of resistivity, but all terms, everything that you've studied for resistivity, it's the inverse of it. This is denoted through the symbol sigma. So this becomes inverse of resistivity, that is 1 by, this is resistivity. So SI unit, resistivity is SI unit we had seen in the last class, it was ohm meter. So conductivity's SI unit will become ohm inverse meter inverse. Fine, now this is conductance and conductivity. First note down these two, then we'll do others as well.
Okay, ma'am.
All right. Now the other two terms. Before moving on to anything else, let's see these terms. Now, one is current density. So questions do come from current density at least. Conductivity, conductance questions rarely come, but from current density you have questions. So current density means the current we have understood, we have studied current in detail, we have seen all the formula for current. If you divide the current by area, or you take current per unit area, The quantity that you get is known as current density. So current density is nothing. Let's say this is a wire. Wire is there, of cross section, some area is there, and this is a wire that you have. This is connected to the cell. Now, I amount of current is flowing through this, and the area of this cross section, let's say this is A. So current density is denoted through the symbol J. This is the current density. So what would be the current density? Current per unit area. That is current divided by A. This is current, this is A. An area of the cross section. Now it's a vector quantity. Current density is a vector quantity. So whenever anything gets categorized as a vector quantity, we have to keep in mind its direction as well as its magnitude. So magnitude could be easily calculated with the help of this formula, J is equal to I by A. But direction, regarding the direction, whatever is the direction for the current, take the same direction for the current density. Current density is actually current only. It's just that amount of current that is staying there in 1 meter square area of the cross section. Then we call it as what? We call it as the current density. Now, apart from this, can you tell me the SI unit of it?
Coulomb per meter square.
Coulomb is the SI unit for charge.
Ampere per meter square.
Ampere per meter square. Yes, this is ampere per meter square. Good. So this the SI unit becomes ampere per meter square. Now current density, two kinds of question come. Either directly formula based, use J is equal to I by A. Calculate current by any method you have to calculate. Calculate the area by any method you have to calculate. Secondly, the question comes to write the microscopic form of Ohm's law. What is the microscopic form of Ohm's law? So whenever this comes, so just write and remember the statement. J, that is your current density, is basically equal to sigma. Sigma was conductivity. Remember, we have done it just now. Multiplied by electric field. This is known as the microscopic form of Ohm's law. J is what? J is the current density. Let me write it.
Ma'am, why is it known as microscopic?
Yes.
Why is it known as the microscopic?
Microscopic form of Ohm's law in this sense, because see, normal Ohm's law is what? Normal Ohm's law is V is equal to IR. Now, actually, there's a derivation for this. That's we are not doing it because it has been deleted from your syllabus for this year and the past years that we had. From I think 2 years, the derivation has been deleted, but this question comes in the exam to write for 1 marker. So we had the full derivation where we started with the Ohm's law, but we took and considered everything for a single electron. In case of Ohm's law, what do? We have the full wire. We have the voltage across its end. We have the current flowing through it. So V gets proportional to I. So that is the macroscopic. That is in a full range scope. When we consider about a very small element, like a microparticle, like an electron, and then we relate it with Ohm's law, so we get this equation. That's why we call it as microscopic form of Ohm's law. It can get clear. If you wish, I'll show you the derivation also, but the derivation is of no use to you. Just remember the formula, and remember this is microscopic form because we are considering a very small section of the wire. In case of Ohm's law, we had the full wire, whatever current was proportional to the voltage. Clear?
Yes, ma'am, it's clear.
All right. So this is current density. This is conductivity. And E is basically the electric field. So there is one more relation as well, one more conclusion that can be drawn. That conclusion is that current density is directly proportional to electric field. So if in the exam you get a question like this, electric field is increasing, what will happen to current density? So obviously current density will also increase. So you can conclude from here that current density is actually proportional to electric field. So expressions can be modified in this way. And one last thing, that was the quantity, mobility. Then we'll move on to a different topic that is very important. But before that, just let's end with mobility also. Mobility is basically drift velocity. You've studied drift velocity was the average velocity with which all the electrons used to drift towards the positive terminal of the battery. So mobility is drift velocity divided by electric field. If your electric field is 1 volt per meter or 1 Newton per coulomb, then whatever is the velocity moving that time, we call it as mobility. How the charge is able to move, or how much the charge is able to move under the applied electric field. Basically, what we have studied for drift velocity, mobility is same as that of drift velocity. You can relate it with drift velocity. Difference just arises with electric field. In drift velocity, we considered some magnitude of the electric field. In case of mobility, we consider that electric field is 1. So you can get just formula-based question from this. We denote it through this symbol. This is known as mu, drift velocity divided by electric field. So this is mobility. This is drift velocity. And this is electric field. This is electric. Now SI unit. See, for velocity, we know it's meter per second. For electric field, you can write it as Newton per coulomb also, or volt per meter also. If you can write anything. So this becomes meter coulomb per Newton second. Or even if you wish, you can write this meter per second is also already there. And for electric field, you can write volt per meter. So that becomes meter square per volt. In any manner, in any wish you wish to write it. So these were little topics that couldn't be covered in the last class. So just note down from here. Note down from here. Any doubts, ask me.
Okay, ma'am.
Done?
Yes, ma'am. Done.
Now, so these are very short topics. Now, this is one of the important topic. Temperature dependency of resistance. This usually comes in the exam, and I think past 4 to 5 years, one question is definitely coming under this topic. Not only from this, are you preparing for any competitive exam, Amin?
No, ma'am.
No, right now. So if any exam you have to appear for, any university exam, anything which has a syllabus, then also this topic gets included. So temperature dependency of resistance. Resistance is what? Resistance formula we had seen, that was ml divided by a n e square tau. Formula of resistivity was just eliminating L and A. That became m divided by n e square tau. This much. Now from this we can conclude that resistance and number density and tau, all these are related, and same goes for resistivity and tau. Now see, in both of these formula, resistance formula and resistivity formula, that's just the difference between length and area. Apart from length and area, do you see any other difference? No?
No.
Only this length and area differs. So when we are considering the change in temperature or how temperature dependency is there, or whenever we are coming this taking into consideration this aspect of temperature, there is no change in length and area. So if length and area remain fixed, then whatever will be the change in resistance, that should be the change in resistivity. That's what it's written over here. For the same temperature involved, there is no significant change in length and area. That's why resistance and resistivity have same temperature variation. It says in this is meant in the sense we've just done now that resistance and resistivity we have done in the last years as well. That resistance and resistivity are related by the formula R is equal to rho L divided by A. This formula also we had seen, and so many other formulas of resistance we had seen. So if resistance is changing by something, then it's not a necessary condition that resistivity should same by the same amount. So this basically says that this line says that length and area are differing or changing very slowly or slightly. So there is actually no change in length or no area. So whatever temperature variation gets involved with resistance, that's the same temperature getting involved with resistivity. Both have the same. It means if temperature is increasing and let's say resistance is increasing, so resistivity will automatically increase. So you just have to consider one thing. Just keep in mind one thing: resistance or resistivity. Just let's say resistance you remember, so resistivity automatically you will be able to remember. So one by one, let's deal with things and materials. So first material is a conductor. Now, in case of conductor, as I've already written prior to the class, that if temperature increases, average relaxation time decreases. And if tau decreases, tau is coming in the denominator of resistance. So obviously resistance will increase. And what did we study right now? As resistance increases, resistivity will also increase. So the graph of a conductor, if you vary the temperature, let's say this is the resistance or the resistivity graph on the y-axis. This is the temperature graph on the x-axis. A temperature is present in Kelvin. This is the graph. So what happens? Graph is basically like this. Initially, it's like this. Till a temperature, it is non-linear. And what is this temperature? This temperature is basically 273 Kelvin, which we call as 0 degrees Celsius. So before 0 degrees Celsius, the graph is how? Graph is non-linear. Fine. Now what happens after 0 degree? Once for a material, if temperature 0 degree or 273 Kelvin, this much temperature has been crossed, the graph becomes somewhat like this. So beyond 0 degrees Celsius, the variation is linear. These graphs will be repeated when we'll be doing semiconductors. In case of semiconductors, no, we will see the mechanism. Why is the conductor having the resistance increase, or why is the conductor or any other material having the resistance decrease, or why is only tau dominating over here? Why are we not considering number density? Because n is also there. I've told you n also varies. So why are we considering only these things? So all these things that will get clear by this only. So conductor is what? Resistance, resistivity varies with temperature. This is one. And for conductor, like you in the exam, questions in your current electricity, like in your UT examinations, or if you have just a current electricity test, then coming of these graphs, chances of these graphs coming into the question, this is less. But this is in your syllabus because this is there in semiconductors. So there we'll see it in detail. But right now, as we are dealing with resistance and all these topics, you have to be aware. Now, alloy. What happens to alloys? Alloys, you must have heard of mixture of materials. Yes?
Yes, ma'am.
Now, in case of alloys, what happens? This is the resistance or resistivity graph on y-axis, and this is the temperature on the x-axis. Variation is there from the normal one. Normal is this. See, if I draw this graph, then I'll say this is a constant, mean resistance and resistivity are not changing. But resistance and resistivity slightly increase. There's a slight increase. Means if this was the original line, which represented the constant resistance, slight deviation or slight increment you are able to observe for alloys. So slight increment or variation is observed for alloys. Resistance and resistivity increase. This is the second case for alloys. Now, the last case, this rarely comes in exam, superconductors. These are some materials. This material is basically known as a superconductor. So superconductors have high values of their coefficients of resistivity and everything that we'll see in today's class only what is meant by this coefficient of resistivity. So basically these superconductors, no, at a certain temperature, they are such kinds of conductors that they have a certain temperature limit. Once that limit is crossed, then only they'll be able to show any variation resistance. Like I'll explain you with the help of graph. Superconductors rarely come in the exam. Mostly conductors, alloys, these come. So let's say this is resistance and resistivity graph on y-axis. This is temperature graph. So till a certain temperature, which we call as the critical temperature. This we call as the critical temperature. The variation is normal. There is no variation in resistivity. It keeps on increasing for that critical temperature only. There's no variation that you're able to observe. Resistance will increase. As this critical temperature is reached or a point is crossed, it increases abruptly. And these are valid only for superconductors. Now, one more thing. This. So for conductors, you have to remember in short that if temperature increases, resistance increases. For alloys, resistance increases, temperature increases, resistance increases, and for both of these, resistivity increases. For insulators and semiconductors, temperature increases, resistance decreases, and so the resistivity decreases. Even if you draw the graph, no, between resistance, resistivity, and temperature, the graph will be like this for insulators and semiconductors. But as I've told you, you're not going into the details because you have a full chapter semiconductors on this. That there, all these things will be there. So graphs you have to remember. Conductor increases, that graph. For alloys, resistance decreases. Yes, Mariam. I'll scroll. What happened, Mariam? Why did you join so late? Others have also not joined. Okay, network issues. All right, so first, Mariam, from here you take the screenshot first, then you can note it down to it. And just keep on writing done so then I can scroll. From here, you just note it down. From here, you also have to write.
Ma'am, can you scroll up a bit?
Done by now?
Yes, ma'am, done.
Mariam?
Yes, ma'am, done.
All right. Now, so as I was telling you, these portions, these are included in your semiconductors also. So when we do semiconductors, there you will see the mechanism also, how electron and that bond breaks, and why do we see such kind of variation with temperature and which factor dominates. And if you get a question from current electricity, only this much will be asked. Otherwise, it will relate it with that semiconductors portion. Semiconductors is actually the last lesson of your syllabus. Now, what kind of questions specifically come from semiconductors are those questions that have the numerical value. Basically, numericals come a lot from this section. So we'll see how numericals come. There's a formula that you have to remember. We'll see a question also, question that has already come in your exams. Variation of resistance with temperature. The formula is basically RT. Now, RT is what? RT is the resistance at a temperature. A temperature is there, like let's say, for example, 40 degrees Celsius is a temperature. So, resistance at 40 degrees Celsius, that becomes the resistance at that temperature T. So, RT is any resistance value at a specific temperature. This is equal to resistance in the room temperature. Resistance value at room temperature. Room temperature basically means 37 degree to 40 degrees Celsius, whatever is the common room temperature taken. So that value of resistance at that point when the temperature is room temperature, we take the resistance value as R with a 0 in the subscript, which we pronounce it as naught. So this becomes what? This becomes R naught. So RT is equal to R naught. Now under brackets, square brackets have 1 plus alpha. Now what is this alpha? You people must have done in your 11th standard in the thermal expansion lesson. Linear expansion, superficial expansion, volume expansion. Did you people go through this? Ever done this?
Yes, ma'am.
Yes, yes. All right. So their linear expansion you must have studied. There was a constant known as coefficient of linear expansion. Similarly, gamma represented coefficient of volume expansion. Beta represented coefficient of superficial expansion. So these expansions are there present. Now, in case of resistance, we have a special coefficient of resistance, which is basically inverse of temperature. Just inverse of temperature in physical properties as well as in mathematical calculations. So resistance, if the temperature SI unit is Kelvin, then coefficient of resistance SI unit becomes Kelvin inverse. That is V denoted by alpha. It's a constant symbol, and for different materials it has different values. For example, for steel, coefficient of resistance will be different. For tungsten, value of coefficient of resistance will be different. For copper, the value of coefficient of resistance will be different. It's a material dependent property. So alpha is the coefficient of resistance. SI unit is what? Kelvin inverse. Whatever is the SI unit that you've studied for temperature, it's the opposite of it. So 1 plus alpha multiplied by the change in temperature. So how can I write the change in temperature? T, that is the temperature, room temperature that I've taken, minus T naught. T naught is the room temperature. This is a formula that you have to remember. By chance, if change in temperature is given as delta T, then write this equation as R naught 1 plus alpha delta T by this. Both are same. If you are comfortable with writing delta T, then you're fine. If you're comfortable by writing T minus T naught, then you're also fine. Both of the formula are same actually. We write the change in temperature as T minus T naught. So that's the temperature. Note down this, then we'll see a numerical. How do numericals come from this formula? For all those who have written no the above question, try this question. First note it down, then try it, then I'll discuss it. At least read the question, write down all the variables, try to put it in the formula, see what's the result you're getting. You'll be able to do. It's a formula based only. And this is from your NCERT and it has come in your CBSE exams. See, in this question, you just have to identify the terms. Like an electric toaster uses nichrome for its heating element. When a negligibly small current passes through it, its resistance at room temperature is 75.3 ohms. So room temperature is important. This value of resistance is important. And when the toaster is connected to a 230-volt supply, the current settles to a steady value of 2.68 amperes. What is the steady temperature of nichrome element? You don't have the second value of resistance, but with the help of voltage and current, you can easily calculate the second resistance as well. And temperature is unknown. Alpha is also given to you of nichrome, that is 1.7 into 10 to the power minus 4 per degree Celsius. See, just check if you get your answer, submit me in the chat box. Are you people trying it? Should we discuss it right now? Do you need 2 to 3 minutes more? What do you say, class? Should we discuss it right now or do you need some more time? Yes, Aman, Mariam. Okay, let's discuss it. Let's discuss it. See, it says an electric toaster using nichrome for its heating element. When a small current is passed through it, the resistance at room temperature, it means this is what? This is the room temperature. R naught is given to us, that is 27 degree, not R naught, T naught. T naught is given to us, that is 27 degrees Celsius. So T naught is given to us as 27 degrees Celsius. This is the resistance at room temperature. This is the room temperature. So what's the resistance at room temperature? It's mentioned 75.3. See, what does the line say? Its resistance is 75.3 at room temperature. So this is 75.3 ohms. Fine. It says when the toaster is connected to a 230 volt supply, means voltage is 230 volt, current settles to a steady value of 2.68 amperes. This is the value of electric current that we get. Now, you have to find out the normal temperature, the other temperature. And alpha is also mentioned. Alpha is what? Alpha is 1.7 into 10 to the power minus 4 per degree Celsius. Now see, of the formula that we wrote and the formula that we studied, we had seen there were two resistances. One was the room temperature resistance, other resistance was at a certain temperature. So that we can easily find out using V and I. What was Ohm's law? Ohm's law was V is equal to IR. So resistance will be what? It will be voltage divided by current. Voltage is 230 volts. Current is 2.68 amperes. This should come around 8, 6, so 40, so 8, 5. And then this will be what? I think 6 around this. If we round off it, it should come out this much. Just check the calculations once again and let me know whether it's 85.6 or something else. So this is the value of resistance. Now you have all the variables with you in line. You just have to find out the resistance value. So resistance will be what? Resistance formula that we have studied. This is simply RT is equal to R naught 1 plus alpha delta T. So RT is mainly resistance at the normal temperature, that is 85.6. Room temperature was, I think, 75.3. That was 75.3. 1 plus alpha is 1.7 into 10 to the power minus 4. And delta T. So T we don't know, T naught, we know that's 27 degrees Celsius. This will be our equation that we have to solve. Now, one thing in this, see, when you solve this equation, you will get the answer around 846 degrees Celsius. Now, one thing, why are we not converting 27 degrees Celsius into Kelvin when we know that degrees Celsius is just the CGS unit, whereas it's not the SI unit? And when we write anything in the formula, we write everything in terms of SI unit. Why are we not putting degrees Celsius? Any idea, anyone? See, the reason is that, for example, I am not calculating just the temperature, I'm calculating the change in temperature. For example, let's say, I asked you a temperature. You told me that the temperature is 30 degrees Celsius. All right, fine. So for my calculation, I didn't use this as it is. I converted into, I hope you people know how to convert 273 plus 30. This is how you write. So this will be what? This becomes 303 Kelvin. I've converted. I asked Mariam, you give me a temperature now. Mariam says 27 degrees Celsius. The temperature that Mariam gives is 27 degrees Celsius. I said, fine. So instead of 30, I'll be adding 27 here. Why am I writing this? Because you people should know when you add 273 to a number, that converts into Kelvin. So Mariam said 27 degrees Celsius. Fine. I agreed and I converted it. So it came out to be 300 Kelvin. Now, when I took the difference between the numbers that you both have told me, what is it? 30 minus 27 is 3, a gap of 3. And when I take the difference between the conversions that I have particularly made, it is also 3. So even if you do not convert it, had I not converted in my calculations, had I saved that time for my other calculations, I wouldn't have been wasting the time. Because when the difference is there, if it's a change that you're calculating or it's a difference that you're calculating, it remains the same in degrees Celsius and Kelvin. So in these kinds of question where you have to find out the change in temperature, no need to convert into degrees Celsius. If you have sufficient time, you can convert. Answer will be the same. As you can see, a gap of 3 was here also, gap of 3 was there also. First, tell me, is this question clear to both of you? Yes, no, do you want me to repeat any query? Okay, it's clear. Now, last thing, before we end the class, last thing is, for conductors, remember that alpha, this value of coefficient of resistance, we have alpha as positive. For insulators and semiconductors, we have the value as negative. Regarding alloys, value is positive, but it's very small. 10 to the power minus 30, this much value, this much small for alloys. For conductors, it's positive. For insulators, it's negative. This is just a data that is helpful when we are solving numericals. Fine, so just note down the solution.
Ma'am, can you scroll down, please?
Done, Mariam?
Yes, ma'am. Now done.
All right. So fine. So I'm stopping.